Hi, hello, and a very warm welcome to everyone. Today, in this session of Technicians, let's see basic coding concepts of linked lists, hash tables, recursions, and pointer by me, Deepthi Anand, BTech IT, second year. So, what are linked lists? Linked list is a data structure that consists of a sequence of data with records or nodes. Each node comprises of two fields, a data field and a link field. Types of linked lists are singly linked list, doubly linked list, circular linked list. Under circular linked list, we have circular singly linked list and circular doubly linked list. Singly linked list, each node consists of a single link to its next node which traverses in only one direction, that is from head to null. Head pointer is the pointer which points the first node in the list, and null pointer is stored in the linked list of the last node in the list, that is, which indicates the last of the list. Doubly linked list. In doubly linked list, each node has two double links to its next as well as its previous. It helps us to traverse in two directions, that is from head to null and vice versa. Each node has three backfields. Backfield link field, which stores the address of the previous node, data field, it stores the actual data value, and forward link field, which contains the address of the next node. Basic operations in a singly linked list: creation, insertion, modification, and deletion. Creation of a list. So, to first create a list, we set the size to get, that is, the size of the node. And in our new node, we allocate the space that is required, and we get the data for the new node, and we set the new node link as null, the head as the new node, and the last as also new node. So this basically creates uh, one node of a list. So to create other nodes, we have to follow the same procedure and uh, just assign the new node link to the subsequent nodes. And then we assign the last link as the new node, and the last is equal to last link. So, and this again helps us to create an other node. To process this, we just carry on the seventh step, that is to continue all the four above steps. So, insertion of a new node. The insertion can be at three places, which is at the first, last, or as an intermediate node. The first node, we have to set the head as null, and the head is set to the new node, and the new node link is set to head. So basically, the head, which is equal to null if it is null. So then we set the head node to the new node. So this is set to the new node, and the new node link is set to the head. That is the one which is already assigned as head. Insertion as the last node. If the head is null, so if the head link is null, we get to know that it is the last node of the present list. So if the head is null, we set the head equals to new node and the last is equal to head. And if that is the last link is equal to null. This whole process takes place only if the last link is equal to null. And we assign the last link to the last link, that is the last of this is assigned to the last link, and the last link as new node, and this last link is assigned as new node. Next is insertion as a middle node. If we have to insert a node between two nodes, so then we just see if the head is equal to null. If the head is null, basically it tells us that it we've got to set it to the new node, and then it helps us to read the insertion where it is made, and then the condition. Again we say if last is equal to head while last not equal to null. The last is said to be head only when the last is not equal to null, that is if the last data is equal to the condition. After that which we assign the new node link to the last link. So this new node link is assigned to the last link. So basically in this, it gets to be inserted in the middle because the previous node, that is the head node link, is asserted to the new node, and the new node link is assigned to the last link node. So that is this link's node. This helps us to insert it as a middle node. Now modification. To modify, we just have to ask the values which is going to be modified. We store that as modify here, and we just say the last is equal to head. Now here comes the thing, while last is not equal to null, so the last is not going to be null, then if the last data, that is if this data is equals to the modify, then we change it. So this helps us to traverse as it is. If this is not, then else, if this is not, go to last link. So if this is not it, then go to last link, that is this one. It reads again here, checks if this is the value, yes, modify B is the value, so then we modify it here. Deletion of a node. The new node can be deleted from the list at 3 points, such as deleting in the first node, last node, and an intermediate node. Deleting as the first node, we say if the head is equal to null, then the list is empty. Of course, if the head is null, which does not point to anything, then the list is empty. Else, the del node is set as head. The head is set as del node here. Then we have to just assign this head to the head link, that is this node. This head is then assigned to this head link. Basically, this node is then just gone. Deleting the last node, it's the same thing, and we check if it's a null. If it's not, then we check the but then we assign head as last, while last link not null. So if this last link is not null, we assign last as previous, as this as previous, and last as last link, that is this one. So then as we traverse it, when once we find the previous link, that is this link, to be null, we delete this. Deleting the intermediate node. Again, if the list is empty, print it. If not, then we take the data node which is required for deletion. So then if the head node, that is the head node's data is del node, then we assign the del node as head and the head link as head. So then as we traverse it, once we find the intermediate node, we get to delete it. Now, the basic operations in a doubly linked list are creation, insertion, modification, and deletion, just like the previous ones. Now, in creation of a doubly linked list, we set the size, allocate the space, and we read the data. Now, here comes the thing. As we have both B-link and F-link in a doubly linked list, we have to take care of both of them. So the B-link and F-link is set as null, and in the new, and the head is set as new node, and the last is also set as new node. And if we want to add another node, we do the same thing until 5, and after that we set the last as f-link, last f-link as new node, and the new node b-link as the last. So the last is set to be last f-link. This goes on, and once we get to add more lists, we just got to repeat it from step 8. Insertion of a node. Here also insertion takes place in three steps, in 3 places: first node, last node, and intermediate node. So inserting as a first node, we say if the head is null, then set head is equal to new node, the same thing as previous. Whereas here we assign the new node's f link as head and the b link as new node. Again, the new node f link is set as head and the b link as new node, and the head is set as new node. Inserting as the last node, if the head is equal to null, that is if the head is null, set head is equal to new node, that the head is just the new node. Else set last is equal to head, then we assign last as head, while last f link not equal to null, that is when the last f link, that is this f link, is not equal to null, assign the last f link to assign last to last f link, that is last is assigned to the last f link, and the last f link is assigned to the new node. So this is assigned to this and this is assigned to this. And insertion as a middle node, first we need to check if the head is equal to null. If not, we set the head as new node, then we enter the node after which the insertion is to be made, and we read the condition, after which we assign the next equal to last f link. The new node f link is set to next, and the next b link is equal to new node. Basically, once we find the condition, we assign next, that is this part, to the new node's f link, so this part is assigned to this, and the next b link, this b link, is assigned to new node here again. Now new node's b link, this part is assigned to the last f link here, and the last f link, this f link, is assigned to new node, and This helps us to insert it in between the condition that has been provided to us. Now, modification of a node. The modification, we as usual get the value that is need to be modified. Assign last is equal to head, while last not equal to null. This helps us to traverse through the list. So if the last is not equal to null, we say we check for the last data if that is to be modified. If the data is to be modified, then we check if it is yes, then we say last is equal to last f link. So this is equal to the f link of this. We get to modify this. Now deletion of a node. Under deletion, we can see that it can be deleted at three places: the first node, last node, and the intermediate node. In the first node, head is equals to null, then the list is empty. As usual, as we check when the list is empty, else the del node is set to be as head. So this is set as del node. Then we assign the head to the head's f link. That is this f link, the head's f link. And then the head B link is set to be null. So then we just get to print the whole thing. The head's F link is updated to this, and the head's B link is updated to null. And then we just assign this, which helps us to get rid of this node. Now deleting the last node in this, if the head is equals to null, then the print list, that is, it is empty. The set last is set to be head, and then the last f link is not equals to null. Assign last is equal to last f link, del node is equal to last, and the last b link to f link is equals to null. So since we have to delete the last node, this one's set to be last, and which is the head, which helps us to traverse through this, and this becomes the del node. So then we set the last f link, this as to be null, and the del node is equals to the last. The last b link and f link is set to be null, since we have to get it to be deleted. Now, to delete an intermediate node, we check if the list is empty. Then we ask the node that requires to be deleted. Now, we assign the head data to be del data. If the head data is to be del data, then set this as the del node. And then we have to basically assign this one's f link to the next node's b link, and this one's b link to the next node's f link. This is what happens when you just have to get rid of this in simple. So let's go through this program. Then we have to just set the del node as head, the del node as head, and then we assign the head f link, and then assign head to head f link, that is this one. And now if the head is equals to null, then we assign head's b link as null. Else the last, that is last, is equal to head f link, that is again this. While the last is not null, if this is not null, then the last data is equal to del data. Then set the del node is equal to last. Set previous is equal to the last b link. So this becomes your previous, and next as the last f link. So this becomes your next. So this is your next. This is your previous. Again, assign the previous f link, this previous f link to next, and this to previous. Stack implementation using linked list are, we can perform three operations: push, pop, and peek. If push is basically nothing, as we know how we used array to insert a new element. We just say if the top is equals to null, set top equals to new node. So if that is basically the head equals to null, then the head equal to new node. Else we just assign new node link is equal to top equal to new. This is basically just to add in new nodes or to push the values into the linked list. Next is pop. Pop is basically deleting an element. So as you've seen deletion, this also follows the same thing. That is, if top equals to null, then print stack is empty. Else set del node equal to top. Assign top equal to top link and del data as del node data. Again, going through it, the top, that is the first element, is set to be null, and the stack is set to be empty. Else we set the del node as top. The top is set to be del node, that is the head, and we assign the top link, that is head link, as top. Which this helps us to traverse to the next one, which helps us to delete the data. For peek, If the top is equals to null, again the stack is empty. This is a condition for to check if it is empty. Else we just assign the value as top, and the top element is set to, and we print the data of that value, which helps us to print the top element. Now, implementation of a linear queue using linked list. So in queue, we have enqueue, dequeue, peek, and display. Basically, enqueue is nothing but push, and dequeue is nothing but pop. So basically, inserting an element and deleting an element is those, and peek is to look into it, and display is display. So enqueue is again we create a new node and we say here is equal to new node. As we know, queue has two ends, front and here. Here is the last and front is the near. As we enqueue, we keep incrementing the rear. So the same thing happens here. So if the front is null, we set the front is to be a rear and we assign t is equal to front while t link not equal to null. So that is when it is not equal to null, it keeps pushing. That is here t equals to t link equals to here. Now dq is nothing but pushing forward the front element so that we can get the del nodes to be out of it data. So again, if we say front equals to null, then print q is empty. Else the del node is equal to front, assign front is equal to front link. So now the del node is said to be the front, that is your first node, and that is assigned to the front link, that is the link, that is the next node of it. So that deleted node is the del node data. Peek operation. Peek is if front is equals to null, then it is empty. Else we just set the value to be front and the front element is printed. That is, it basically displays the front element's data. Display. Display is used to display the whole list. That is, again we check if it's empty. If not, we run a loop that is from front, the first node, to until it's not equal to 0. That is, the t link is not equal to 0, which helps us to print the data of t. Now, one of the applications of list are polynomial manipulation. As we know in polynomial manipulation, this includes for addition. Here, what we do is we take the corresponding biggest biggest part that is required, and we take the corresponding coefficient of that to be added and then display the answer. So that is what happens. So we set the size, which is, and then we set the new node. Now we have new node to read the coefficient as well as the exponent. So the new node link is equals to null. If we we set the new node link to be null, and that if the head is equals to null, if the head is equals to null, then we say new node exponent if the new node exponent is greater than head's exponent. That is, we compare the two exponents, and if it is, then we assign the new node link as head. Basically, we just assign that to be head, and since we have to get the largest exponent possible, and the head is equals to new node. Else we set the last is equal to head while the last link not equal to null, and the last link's exponent is greater than new node exponent. So this takes care of whichever exponent it to be greater, and then we assign that as the head or last link. So then the new node link is last link is equal to new node. Now, coming to the next concept, that is hash table. First of all, what is a hash table? Hash table is a data structure that is used to store keys or value pairs. It uses a hash function to compute an index into an array in which an element will be inserted or searched. Basically, hash table helps us to insert elements into it which can be searched. It's basically a faster searching technique. So we have a factor called the load factor, which is denoted by the symbol lambda, which is the which goes as number of terms in the table slash the table size. How many ever terms we have slash table size. Let's assume we have a table size of 10 and consists of 6 elements. So your load factor, that is lambda, will be equal to 6 by 10. Now, a good hashing method, it includes of executes quickly, distributes the keys equitably, has less collisions. So what are these collisions now? These collisions we still try not to have collision, but these collisions occur when two or more elements have the same hash value, that is the same load factor value. And there are ways to handle this collision, such as linear probing, quadratic probing, and separate chaining. In collision resolution, under that we have open addressing, which consists of linear probing and quadratic probing and chaining. So first, separate chaining. Let's say we have a hash function which has a key mod 7 and sequence as 50, 776, 85, 92, 73, 102. So then we try to insert 50, which we get 1 using the load factor. So this will be a 1. And then when we after that we insert 776, we insert 776. Until this we are all good since we have no collision. Now when we try to add 85, we get the same value as 1, but we already have a value at 1, that is 50. Now what we have to do, separate chaining says, add another block and add 85 as the next block element. So basically we have separately chained the element of 85 to the same address space that it requires. Now coming to 92, again 92 provides us with a collision which occurs as to adding to the chain. That is now 50 to 85 and 85 to 92. Now again we have 70, sorry, we have 73, yes. 73's value is 3, but we already we already have inserted, but even 102, sorry, 101 gives us the same value as 3, so we insert that over here, adding a separate chain. So this chaining separate nodes the same index value gives us the whole uh, chaining method, that is to keep on adding chain to it. Next is linear probing method. Now, let's take this example. When we insert 76, we've used a key mod 7 of index valuing. So, mod 7 of 76 gives us 6, we've inserted. 93 gives 2, we've inserted. 40 gives 5, we've inserted. Until this, we have no collision happening. But here, we have 47 mod 7, which again gives us 5. So, in the place of 5 we have 40 already. So what we do here is we go to the next element, but here we don't have space. Again from here the next best free space was 0, so we insert 47 at 0. Now going to 10, we have free space at 10, so we insert it. Now 55 we go to 6, but at 6 we already have 76. We go to the next space, that is 47. 47 already also has a thing. The next free space was at 1. So hence we insert 55 here. Next, these are the functions for resolution again. Now if the hash mod s is full, then we try hash plus 1 into 1 into mod s. That is, if key into a key mod s is full, then we try hash plus 1 into 1 mod s. Now, if that is also full, then we try 2 into 2. If that is also full, then we say, then we try 3 into 3. We repeat this value until an empty slot is found. So let's say we have a key function mod 7, and these are the elements. We have an initial element, and when we do 50 mod 7, we get 1, we insert. 700 and 76, we get 0 and 6, we've inserted respectively. And then now the collision occurs for 85. Now 85 gives us the same position as 1, but we've already been filled. So we inserted it as 1 plus 1 into 1. So that gives us 2, this position. This is the basically like a formula, which is 1, that is the hash value of the original, plus the into the I value, that is 1. Again 1 into 1, which gives us 2. Now on insertion of 92, again it occurs at 1, but we are already full, so we say 1 plus I value is at 2 now, so we say 2 into 2. So 2 into 2 is 4, 4 plus 1 is 5, so we insert that over here. Now we insert 73 and 101, which occurs for no collision. Now, what is recursion? Out of this, the process in which a function calls itself directly or indirectly. Recursion is basically when we need a function to happen over and over again, and we need to keep calling that function. Example, we need to add no, let's say we need to traverse to trees or Hanoi, towers of Hanoi problems as it's given here. We need to keep calling that function again and again. It is impossible for us to write that function for n number of times, since we don't know what could be our n and what could uh, and how many times that n could be. So when we say recursion, this function which calls itself again and again, when we say call yourself again to solve this problem, it reoccurs again, it reoccurs. So this helps in recursion. Now, as I said, there are few problems, towers of Hanoi, traversals, and such. So in traverse, so first let's look at towers of Hanoi. What is tower of Hanoi? The tower of Hanoi is nothing but uh, changing of these discs, the three discs, to tower C with the same order, that is the biggest, medium, and the smallest. This order is always to be formed. We cannot put a big uh, disk over a small disk. All these three should be assembled in the same way in the tower C. So that is basically the definition. Basically, arranging of all the disks in tower C without any disk being on, without a bigger disk being on top of a smaller disk, in any conditions as such, not only in the final condition, but in any condition as such. So in one disk, we have uh, this one. So for directly, if it's only a one disk, we can directly move that from A to C. We have nothing to think about here or nothing. Again, if it's two disk, we can move one disk to B, the smaller disk, and the bigger disk directly to C. And then this smaller disk is moved on top of C. So basically we will have something like this in the top after arranging these two disks over each other. So again, as it says, move a disk from A to B using C. So there will be two disks here. Uh, this one disk is moved here, the bigger disk. Now, and this disk is directly moved here. Again, after this procedure, we move this disk to here. So move a disk from A to B using C, and move a disk from A to C using B to C using A. This is what happens. Now, three disks. Now here is where uh, the problem occurs. So now we have to move two disks from A to B using C. That is, we first put the smaller disk to C. So let's say we have our a small disk here, and now the medium sized disk goes directly to B. Again, we put the smaller disk which was in C back on B. So we have the medium size disk and the smaller disk, and now this big disk is directly going to C. And so let's get rid of one. Yeah, so let's get rid of this disk, and rather we'd have a bigger disk. Now we have to arrange these two disks. Now these two disks cannot directly go here, since we need to follow the size appropriately. Now what we do is we put the small disk back to A, since we won't have all these disks now. So we'll have only a small disk, and the medium size disk goes to C, and this small disk goes again to C. So at last we have the big disk, the medium disk, and the small disk over here. So now to call that function, the function needs to be repeated again and again. So here we say we initialize the elements. If n is greater than 0, n is the number of disks. Then we read this to n minus 1, A, C, and B. Now we move the disks and then we read it to n minus 1. Basically, it calls it back and back again to this function. So this keeps reoccurring, so the recursion occurs here. Tree traversal. As we all know, there are three types of tree traversals possible: pre-order, in-order, and post-order. So, pre-order, we first travel the root node, then the left subtree, and then the right subtree. So, if this is our tree, during our pre-order, we first traverse the root node first, then this is second, and this is third. Now, to proceed to perform this, we check if the node is not equal to nil. So this node is not supposed to be nil. Then we print the data of the node. We print this data. Now we call the pre-order traversal, which is calling the left child of the node. That is, this child of the node is called. Next pre-order traversal we call the R child. That is this child. So in this case, we only have one parent with two children. But in cases of having huger trees like another one here or so and so, this would be called again and again to print the pre-order traversal of this. Now, for in-order traversal, let's say we have the binary tree. Again, we have to traverse through this. Yeah. For this, we traverse the process is traversing of left. So this goes first, traversing the root node. This is second, and this is third. So left, root, and right is our order. Now we again check if the node is not equals to nil. Then first we call the left child here. Then the data node, that we print the data of that node, and then we call the right child. So this helps us to print the order in this way. As we saw for pre-order, if the length of the tree, the size of the tree was more, then it would have been called again and again to print the various size. So to print the various to print the in order of various trees or subtrees present in this. Now, for post-order traversal, we have to traverse to the left subtree. Again, let's take a tree, left. Yeah, so this goes first left, then this right, then the root. So here it is left, right, root. So then if since we traverse it to the left subtree, so we call the in-order traversal of the left child, and then the right child, and then the data of the node. The node is always the parent. Please remember that when we print the node, it prints the parent. Here again saying it's only for one subtree, sorry, one binary tree. We could have trees of various lengths, so this would be called again and again to process that. So let's see here. As we know, the pre-order traversal for a thing is root, right, left. So what is the root node of our thing? It goes as A, and then we have the right. Sorry, we have the left. This would be left and right. I'm extremely sorry. Yeah, so this is a left. Coming to left, we have B. But when we see that, after we write B here, when we see that we have another child, so we write the left. That is this, D. Now the right of this is E. When we go to B, the E is considered. Now we go to A. The right of A is C, but C is a parent node, which again has two child, F and G. So left and right. Now coming to Coming to in order, we have left, root, right. So again, when we say left, we go to the deep end, that is this. This is our deep end left element. So D, root of D is B, and the right of this is A. So this goes to E, and now this subtree is over. So we take this whole thing to be the left of this whole thing to be the left. Now A, we go to A. So this left is done. We go to the root, that is A. Now we go to right. When we go to right, there is again C, F, and G. So we go to the left end, that is F again. Root is C, and then the right element is G. Now let's do the post order traversal for this. In post order, our thing is left, right, and root. So under this, the leftmost element, as we say, left, right, root. Until this, it's clear. Now again, when we go to the left of this, we see that this root, but this root already has another subtree towards it. So again, we say this one. So left, the root goes down. So left, uh, right, root, and then this goes to the root. So left right rule, so we go to the left, we finish this tree, and then right, when we go here, we have this one, we finish this tree, and then we go to the root. The last topic, that is pointers. The pointers are one of the core components of the C programming language. It can be used to store many memory addresses, sorry, it can be used to store memory addresses of other variables or even pointers. These use memory accesses, dynamic memory allocation, and many other functionality in C. So now, what is a pointer in C? A pointer is defined as a derived data type that can store the address of other C variables or a memory location. We can access and manipulate the data stored in that memory location using pointers. What is a syntax? Syntax is, we use a dereferencing pointer, that is basically our star operator is known as a dereferencing operator in this thing. So then data type into PTR, that is data type star PTR is the syntax, where PTR is the name of the pointer and the data type is the type of data. So basically this can be in, float, or anything. So this syntax is used to define a pointer to a variable. We can also define pointers to functions, structures, arrays, etc. Now, how to use pointer? We use it to pointer declaration, initialization, dereferencing. Pointer declaration, as we've seen, we use the dereferencing operator int in star ptr. So sometimes we declare will point to some random memory address as it is not initialized. Such pointers are called wild pointers. Pointer initialization. Now, when we use this, we generally use and, which is the address of operator, to get the memory address of the variable, and then that address is then stored to the memory, to the pointer variable. Sorry. So we've initialized var as 10 int. We have declared. Now we have to initialize. So we've initialized the pointer to the address of var. So and gives us the address of the variable. So now here we can declare and initialize the pointer in a single step also. So here we've declared, that is into ptr, this is equal to and of var. So here it initializes, so here it declares and here it initializes. Now, pointer dereferencing. Dereferencing a pointer is a process of accessing the values stored in memory address specified in the pointer. We use the same star dereferencing operator. So we use the star operator, the dereferencing operator. Let's look to an example. we have had include, void, we've initialized. Now let's declare. So we've declared using a dereferencing operator. Now here we need to note that the pointer variable and the var, the variable that needs to be initialized, both need to be of the same data type, same data type. So now we assign the address, as we all know, and assigns the address to the PTR. Now we print the value at PTR, value at var, and the value at this. So now let's go through this. Let's say our var is 10. So the value at PTR, where is our PTR? Here. Our value will consider the address. So let's say the address is 101. So sorry. Yeah. So this would give us the value of address, which is a PTR, which is the address. So this is 101. And let's say that, and then we have the value at var, which is 10. We've initialized 10, and the value at point, the pointer here, the pointer gets pointed to this, so we'll have 10 again. So the advantages of pointers are, the we usually use pointers in C programming only. This helps for dynamic memory allocation and deallocation. So an array or structure, this can be accessed very efficiently with pointers. It saves us a lot of time, especially. But there are few disadvantages also. They can be vulnerable to many errors, so which could cause us memory corruption if it is an incorrect value that is provided. And it is a little complex to understand. It takes some understanding and some time for us to understand um, pointers, since it's only used in one language and the syntax is a little hard to understand. What we saw previously was just very simple and basic pointers, but when you run for a bigger area code related, we use pointers on a major level, especially when we use it for structures or arrays. It can be a lot of things that need to go in, a lot of understanding that's required for us to use it very efficiently. So to conclude, let's say the pointers, they are very capable tools which provide see its distinguished features such as low memory access and referencing. As I said, C is the only language which has pointers, so it can have low level memory access and referencing. But as powerful as they are, they should be used with responsibility, as they're one of the most vulnerable parts. If pointers are not used properly, there can be thrown a lot of errors which can be hard to rectify, since one does not have enough knowledge about pointers. But if they are used um, efficiently, they can be used to understand low level memory accesses, which is very useful to make sure our memory stays in place and make sure our memory is allocated with only enough memory required, so which does not waste memory, which is very helpful in a higher level programs, and which helps us to reference, especially. Yes, very important. So as we know, pointers are very powerful, which can either put the program up to another level or bring the program down to a great level. So it needs to be used properly and very uh, efficiently for it to be used to its maximum. So this is it. I really hope you guys understood this session and found it interesting and valuable. If there are any comments, please let me know. And thank you so much for this great opportunity, and hope you are liked.